Hi, greetings again. In this tutorial, I'm going to discuss further about the data analysis of the results that we obtained from our previous simulations. To remind you, we are doing analysis of an ideal single-phase inverter, as you can see here. We considered the ideal switches in this case, since we are particularly interested to look on different type of simulation cases that we can, for example, consider a variance of the modulation index or any other type of parameter that we are interested in. In that case, how to proceed was the main target. So we ran a number of simulations, 40 or 36 in total, that was in the previous simulations, using this script, and we also plotted the fundamental component of the output voltage of the inverter in relative to the modulation index. So to remind you, let me plot the graph first. So here it is. In that tutorial, we saw that to a certain value of modulation index, which is 1 in this case, the relationship of the output voltage is linear. As we can see, if MA is running from 0 to 1, the output voltage, this is the output voltage of the fundamental component, is linear. Now from that point it starts to bend. That means the saturation effect takes place, and the final value is going to be 125, so I think it's a factor of 1.27 in total if you take the per unit value. So I would like to continue the discussion from here. You saw that in the problem description, so let me bring back that, there was also the THD calculation, the total harmonic distortion. We will also see how to calculate this one both for the voltage and current of the inverter. And we will shortly compare the results calculated given in this table 8.4. And we'll also see how it's simulated. So this was the simulation setup we considered here. I ran the simulation again for 40 microseconds so that we can reduce the time that is taken to run all that simulations. I can run it here, but I just saved the results. You can watch the previous video how to do that. So here was the plot of MA versus, for the modulation index versus the fundamental component of output voltage. So here let's write the code to calculate the total harmonic distortion for a single case. That means if we have a particular value of modulation index, how to do it for that, and then we'll see for all the batch simulated results how to do the complete calculation. I would like to call this one, okay, let's just save this. So THD. Just set the window, close all. So for some user settings, I would take the data folder that I created, and I need to provide this one. So we saved the values that you see, all the .mat files are saved here. I'll copy the path. I'll take a variable that is helpful to input what variable I want to plot. So let's call it a variable prefix. Say I start with the load current, of course. I can change it to V out as well. And since we have 36 cases of simulations, we have to provide also what case we want to take. So I call it case index. Say start with 8. Let me clear this first. Okay. And we want to save the results. Now this is the part where we have to input each file, or in that case it's one particular file. So let's call it a file name, which is the full file data folder %s underscore %d dot mat. So it will give us that notification as well. Not here. Did I forget? Yeah, apostrophe. Dot mat. Then we can say the prefix. Then case index. So this is the end of this line. And we can say data is equal to load. Text data, the first variable in the file. So let's call it data dot one. Now let's extract the time and the value of the variables that we are interested in. So first one is, let's take x data dot time. Since the variables are set as time series, so this is the way to read the data. And x should be data. It's also a good idea to show a message on the MATLAB workspace of which data is loaded. So for this, let's print f loaded what is the message then? So we need to show which data or which mat file is loaded. d.mat, and this is the prefix and the index. All right, then now for the calculation again, we need to put some parameters that we defined in these previous simulations as well. So this one we can just copy. So if the frequency, fundamental frequency 50 Hertz, period is calculated as 1/fb. Starting time we take 20 milliseconds and ending time is after 1 period. L was an auxiliary variable for the calculation of the Fourier coefficients for our case. And we also had one variable called Hmax. So let's take 50. So Hmax is the maximum number of harmonics that are included in the calculation. Now for our calculation further, we need to extract one steady state value. So extract steady state period. let's first identify the index of this. So it is t greater than t start and t less than or equal to t end. T is equal to t I dx, and x is equal to, so x is a general variable that can be current or voltage or any other variable. Now in the signal itself, be it voltage or current, there is also a DC part if we do the analysis. So for the spectrum of the frequency spectrum, we want to leave that DC part since we're interested in the AC signal analysis. To do that, we need to subtract the mean value or the average value of x from x itself. So the DC part is now removed. So let's compute the harmonics now at this stage. So I just saved the file in the meantime before, if something crashes, it shouldn't be lost. So for that, I will also modify the previous function that I wrote. In that case, I will do it here in single window. Let's call it AN, BN, and HN. So these are the Fourier coefficients, HN. And I will write a function later that, let's call it compute harmonics. And as input, we have to provide the properties of the signal that we created. That means the time. We have to provide x, number of frequencies, and L. And to find the total harmonic distortion, as you know from the definition itself, we need to have the fundamental component in RMS value and the total harmonic parts in RMS values. So with V1, I will just call it V1, let's call it X1 for general terms. If it is current or voltage, I don't know, but so HN first one, since it's the fundamental component, and XH is then, I include also the fundamental component, the harmonic part, so that we can see the complete spectrum of harmonics here. So I will just call it all components. And to calculate the THD, it's once the square root of sum of the harmonics. That means it starts from 2, from 2 to end, and element-wise square is the square root and divided by x1. Since we're having a fundamental component as well in x, so we start from 2. That ensures us only the harmonic components are included, not the fundamental component. And of course, if we want to show the results in terms of percentage, we should multiply the whole thing by 100. So let's print numeric results. So fprintf. So harmonic analysis for this two, fprintf Let's take fundamental component. X1. And it should be, let's 0.3f. Of course, we need an RMS for the calculation. And to show them, it is x1 divided by square root of 2. Because here we have the amplitudes. So to get the RMS, we need to divide it by square root of 2. I think until now it's clear to understand. And finally, there is one more variable that we need to include. So it is suggesting me to include the total harmonic distortion. That's correct. That's what I also want to show. Now let's plot the results. I'll take 1, 2, 3, I think 4 plots. So it's 4 plots. So subplot. First, let's see the signal Tx, and let's take a line width of 2. 2 might be too much. Let's take 1.5. Let's label, then we have time. Or a label. We have printf s suffix. So we can add a title specifying what this is. So I'll call it time domain plot of waveform, and we need to specify what type of waveform it is. It should be automatically read as we specify above. So let's call it %s case %d, and we should get out of it and we'll prefix case index. Read on. So I think we're ready for the first plot. Let's see if everything is fine. 29, line number 29. X is xidx. What's missing? Invalid expression. Why? idx. Check for missing multiplication operator, missing or unbalanced delimiters. 29 is this. Instead of parenthesis. No, should be okay. So I see it's not, it's column 29, but the line number is 45, so it's not 29. Let's go to 45. Okay, I think I'm missing a comma here. Yeah, it seems to be gone now. Let's try. We have another. Using THD as both the name as variable and the name of the script is not supported. So what am I doing here? THD. I didn't know that. So the problem is I named the M file as THD and as a variable as THD. That means it's not supported. Something new to me. So let's save it as THD. Let's call it VI. So voltage and current. Now let's see another. Okay, yeah, of course. This is correct. I didn't define the function itself. So this is what I always forget. So let me define the function. I think I call it compute harmonics is the name. And as outputs, we had 3 variables. And these were an, bn, hn. And as inputs, we had t, x, hmax, and l. I didn't want this autocomplete. So let's pre-allocate the variables. An as zeros, then we had 1 hmax, bn, I'll just repeat the formula. Then we had cosine of n times pi times t by l. The same thing we had, there was a suggestion, I missed it. So this is for bn, and we need to change it to sine. So this is the end for this for loop, and we need to assign. So this is fine. Is it a tab? Yeah, tab means auto completion. Nice. And we had end. I think now it should run at least, right? No, it's not yet. Sorry, but let's see. The end operator must be used within the array index expression. To end, square root. Yeah, but from what? That's the problem. I need to specify the signal itself as well. This is not good. Where is it? THT. Sum of it was XH, right? Sum of XH. Yep, it's running. So you see we have one period. For one period, so 16 milliseconds from point 2 to point, and for this point 36. So we can go with the rest of the calculation and plot them. So here I can start from here. The second one should be, I would like to plot the frequency spectrum in terms of frequency, and along the y-axis we can plot the amplitude. So let's do that. So frequency axis, I would call it 1 to h max, and let's multiply it with fp, which is the fundamental frequency, since I want to plot the x-axis as hertz. And then bar frequency axis xh. Oh, this should give us then, let's read on, let's plot this. What is a partial unrecognized property? This is not good. So excuse me. So the problem was again with the labeling of the first plot. So the title of the first plot. I missed a point somewhere. Again, the typing mistake. That's why I like to do it offline, so that I don't take too much of your time. So here is title is now corrected. We have the grid on. The second plot, if we just plot it, we should see a bar plot of the frequency versus the harmonic spectrum. So here we have this one. Yeah, let's name the axis first. So X label, I would call it amplitude. Y label, frequency in terms of hertz. So at this one, I would like to show the same plot as well, but in terms of the order of harmonic. Sometimes it's helpful to show them. 3. And in that case, it's really easy to show the bar plots. It's 1 to H max. So this part, it's 1 to H max, for example. And here we need to change it to order of harmonics. So let's call it N. The third plot. So here, for example, the first one shows us in terms of hertz, 60 hertz, and the second one should show us 1. So its order is 1, the fundamental component, and so forth. It's 21st harmonic, it's 1260 hertz. And finally, I want to add the THD as well. It's not a real plot, but it's better to show them as well. So it's a plot. So we have 4, 1, 4. And let's plot it on that 1 point. So it's 2, not 1. THD. Yep. So the THD level is shown here. So it's 8.7, for example, you can show here. So this is the procedure to find out the total harmonic distortion. Important here, since we're not using the FFT of the signals to find out, but using the manual, so to speak, the classical way of Fourier analysis to find out AN and BN, we have to provide one specific time period, which is shown here in time domain, the first plot, first window of the plot, and then we go for the coefficients to find out different harmonic spectrum. For our case, you can see it is a peak value of 6.38. We can go there, and 6.38, for example, for the current. It was for the modulation index of 0.8. And this 0.8, we had this current as peak and peak value. And as an RMS, you can see from the... So here it's also written harmonic analysis for load 8. It represents 0.8 MA. Fundamental component is 4.5, which is actually the peak divided by square root of 2, and total harmonic distortion is 8.98%. This is good. Now for the rest of the calculations, here let me show you. If we just select V out, then it should plot that output voltage for that particular case 8. And remember, we had a THD of 125% for that case. And if you really want to check, you can go there that we had the fundamental component to be 80 volts. Here, as a quick check, go there. So fundamental component was 80 volts for this particular case of MA. Now, since we are having a code that is running for a particular case, we can now extend this to loop for all of the cases that we did. I don't want to go from scratch again, so I think I have the code here written already. It should be somewhere. This one. So here's the whole code again for current, for example. This is exactly what I wrote before. Yes, importing total harmonic analysis here. And I'm just putting the previously written code inside a for loop to read all the files that we have. Calculation. Yes, everything there. Additionally, I also have noted the harmonic components for each case, the total harmonic component and fundamental component, that allows us to calculate the total harmonic distortion from the graph. So we can quickly read the values from the graph and calculate by hand for one particular case from so many number of cases. Or it can also be shown on the MATLAB workspace here. So we will see for what particular case what are the values for fundamental and harmonic components and what are the THDs. So here is the setup for axes for different type of plots here, left and right. It's also a good idea if you want to further use your plotted figures for reporting and something to plot them. I usually take a PDF version of that so that it's readily available for observation. And in case we need to read some data, I also save it in terms of MATLAB figure file. And then here at the end, we had the function that we just saw. Let's run this. So you see in the workspace. So let me show you the workspace. So here's the workspace. So I specified the load current, for example, and it calculates for what particular MA we had the load current, RMS value of fundamental, RMS value of the harmonic content, the total current, which is the geometric sum of the previous two, and total harmonic distortion. Don't get scared if you see this THD for the first case. This is because we have a modulation index of 0. That means we don't have an output voltage, and that gives us infinite THD. So it's mathematically a garbage value, but you see it here. And then from point 1 it starts to decrease. That means we're now landing somewhere meaningful from the next step. I didn't include this here though in the plot, because otherwise it gives an infinite value and we don't see this value. So for this current in this plot, what we see are quite important, because here we have the results for all simulation files. We can check, for example, one known case for us, which is where MA is 0.8. So if we click here, we see Y value is 4.5, which is the current value in terms of ampere, and it is an effective value. Let's check it. So here, effective value 4.52 is the fundamental one. Yes, 4.52 for this particular case. We can also check the amplitudes. It's just 4.52 times square root of 2. What we also can check is the total harmonic distortion for this particular case. it is also calculated here is 8.7%. If you go down here, the red one represents the total harmonic distortion. You see it's 9.1 or 9.07. The reason is we are taking for our calculation the number of harmonics to be 100. So if we set it back to 50 or even lower value, you should see a change. Now 6. Now we see it's 8.97, which is also here at almost 8.9 or 8.7. And it also specified, there is also an instruction in the book itself. If we include the currents through n is equal to 100, then it should give a slightly higher total harmonic distortion. That means the more number of turns we take, the more accurate will the result become. So let's set it back to 100. So we have a more accurate result of the THD. So it's the plot here. So if you don't want to read the value from the graph itself, you can do it here. So if you go MA is equal to 0.8, so this particular line, we had the fundamental component 4.517 RMS, the harmonic component 0.4. If you geometrically sum them up, you have a total current value of 4.535 amperes. If you just use the formula for THD, it's 9.07%. Now, if you want to do it for the voltage, for example, you just go there, change the variable to be out, run the simulation, wait for a couple of seconds, so you are done here. And let's check the value here again. For voltage, for 0.7 or 0.8, we have 56 volts, which is 80 divided by square root of 2. Is it correct? 80 divided by square root of 2. Yeah, 56. This one represents the total voltage, total RMS voltage, and here is our THD. The curve in green is the saturation curve that we plotted earlier. So this way you can do the analysis much flexible way. Now if you want to change other parameters here, for example in the simulation, let me try it for you. So you go there, you said you need for another case or particular case, it's something changed in your design and you want to see the results instantly. Say if you want to take, instead of frequency modulation 21, you just take 15. You just write here, run the simulation, wait until it's finished. So you see the steps when the simulation is being run. Give it a moment until it's done. You can check the plots also being updated each time the simulation is complete. A couple of more simulations to run. Let's wait a couple of more seconds, then it's done. 33, 4, 5, 6. It should also give a message that it's finished. Okay, I didn't include the message here. Now if you go there, so if you the updated results will be saved in your folder where you defined it. So it's output directory. It's saved there. Now if we run the simulation, not the simulation, the script, the voltage output. Now we should see the MF is 15, so it's updated from 21 to 15, for example. And you see the results are already available for your analysis there. So this way, I think this is much more effective way of simulations. So we have the results ready. You have the modularity. You can port the code to other simulations, and for your task, you can adjust them. So this is one of the ways to show you how to proceed from a simple topology of circuit to an advanced way of data analysis. And this is in practice often the case that you have to handle a lot of data. And that's why it's a clever way to choose a programmatic approach instead of doing an Excel-based calculation or hand calculation, which is a nightmare. I'm sure you will agree. You will agree with me. But since we are considering different topologies of converter technology, we will continue our discussion with more advanced topics. If you have a particular questions for this tutorial, please let me know. I will try my best to answer. And it's since I'm also learning by doing this, if you find anything that's not in harmony of technology, which is not correct, just let me know and correct me if you find something not in order. Thank you for watching, and we will see you in the next video tutorial.